You ever flip a switch and just expect the light to come on? Of course you do. We all do. But behind that simple, totally reliable action, there is a constant, high-speed battle being fought inside our power grid. It's this invisible war against chaos, and it's waged in milliseconds. Today, we're going to pull back the curtain on the silent guardians that keep our entire world electrified.
All right, so here's our journey. First, we'll talk about what happens when the lights go out. What's the real enemy here? Then, we'll meet the grid's own immune system, the heroes designed to fight back. We're going to see how it's a constant race against time, and then we'll get into the secret weapon that makes it all possible. We'll even see it in action with a real-world stress test. And finally, we'll wrap up by talking about these silent guardians who are winning this battle for us every single day.
So, what are we really up against here? Well, the villain of our story is something called an electrical fault, and it's this constant, incredibly dangerous threat to the stability of the entire power grid. Now, what's really wild here is the speed. A fault is basically like an internal lightning strike. It unleashes this massive surge of energy. And here's the kicker. If that surge isn't contained in just a fraction of a second, it can destabilize the entire system. We're talking cascading failures and huge, widespread blackouts. And look, we're not talking about some abstract sci-fi problem. These faults happen all the time, and they're caused by really ordinary stuff. A squirrel climbing on a transformer, a tree branch that sways a little too far in the wind, or just a good old-fashioned lightning strike. Any one of these things could trigger a major outage, which is exactly why the grid's protective system has to be on alert 24/7.
So, how does the grid fight back? Well, it has this incredibly fast and powerful immune system. It's like a team of first responders that just leap into action the second a fault occurs. Let's meet the key players.
First up, we've got the fuse. This is the simplest, most old-school form of protection. Think of it as a firefighter who makes the ultimate sacrifice. When a dangerous amount of current flows through, a little metal strip inside just melts, instantly breaking the circuit and stopping the fault cold. It saves the day, but yeah, it's a one-shot deal.
Next, you've got the relay. Now, if the fuse is the firefighter, the relay is kind of like the 911 dispatcher. It is the brains of the whole operation. It's constantly monitoring the electrical flow, and the second it senses the unique signature of a fault, it doesn't jump in itself. No, it sends an urgent signal to the real muscle of the system.
And that muscle is the circuit breaker. This thing is the heavy-duty, reusable firefighter. As soon as it gets that trip signal from the relay, this powerful switch physically opens up, breaking that massive fault current with incredible speed and force. And the best part? Once the danger is gone, it can be reset, ready for the next emergency.
Okay, so we have all these amazing devices, but just having them isn't enough. The real magic, the real challenge, is getting them to work together in perfect harmony. It's this super high-stakes race against time where teamwork is literally everything. See, the system is designed with layers. You've got your main protection. Think of that as the local fire station, right next door to the problem. It's designed to respond instantly. But what if it fails for some reason? Well, that's where backup protection comes in. That's the fire crew from the next town over. It sees the fire too, but it's programmed to wait just a moment to give the local guys a chance to handle it first.
And this brings up a pretty logical question, right? To be extra safe, why not just have every single circuit breaker in the area trip all at once? I mean, wouldn't that guarantee the fault gets stopped? Well, yes, it would, but it would also create a way bigger problem.
This is where the principle of coordination comes in. And honestly, it's brilliant. So, a fault happens. Every nearby relay sees it. But here's the trick. They are all programmed with slightly different timers. The one that's physically closest to the fault, it has a 0-second timer. It acts instantly. The next one down the line might wait, say, 1/10 of a second. The one after that, maybe 2/10. If that first one does its job and clears the fault, the other relays sense that the problem is gone and they just reset. It's genius. It isolates only the broken part of the grid, which is how you contain what could be a massive problem and keep the lights on for everybody else.
But hang on. How on earth do you calculate those perfect split-second timings for thousands of devices across an entire city or even a state? The complexity is just staggering. And this is where modern engineering gets a seriously powerful digital assistant.
I mean, just try to picture it. It's like trying to orchestrate a symphony with thousands and thousands of musicians, where every single note has to be timed down to the millisecond. Trying to do that by hand, with grid conditions that are changing all the time, it's just a recipe for disaster. The risk of one tiny miscalculation is way too high.
And that is exactly why engineers turn to incredibly sophisticated software like ETAP. That stands for Electrical Transient and Analysis Program. The easiest way to think about it, it's like a flight simulator for the entire power grid.
So what this software does is it creates a digital twin, a perfect virtual replica of the real-world power grid. And inside this simulation, engineers can just unleash all kinds of virtual chaos. They can simulate a lightning strike over here, a tree branch fault over there, and instantly see how the whole system responds. The software then crunches the numbers and calculates the absolute perfect time settings for every single relay to make sure that delicate dance of coordination works perfectly every single time. It finds problems before they even happen in the real world.
Okay, so let's see how this incredible tool is actually applied. Because this isn't just theory, right? It's actively being used to protect critical infrastructure all over the world.
A really great example of this is the Cuckoo substation in Khartoum. A few years back, engineers there used ETAP to model their entire substation, running a full-scale analysis to optimize its protection system and make sure the coordination was absolutely perfect. So the engineers had three main goals. First, they wanted to achieve selectivity. That's a fancy word for making sure only the right device trips. Then, they wanted to ensure reliability, so they simulated all kinds of faults to prove that both the main and the backup systems were ready to go. And the final result? A system that was proven to minimize outages by clearing any fault with, surgical precision.
So, when you put all of this together, all this high-tech analysis and brilliant engineering, you get a result that is both unbelievably powerful and, if everything goes right, completely invisible to the rest of us.
And just to really understand the power we're talking about, get this. A single fault can unleash over 3,000 amps of current. That is an immense, destructive wave of energy. But thanks to a perfectly coordinated system, that entire event can be detected, located, and isolated in milliseconds. A potential citywide blackout is stopped before it can even begin.
So, really, the next time you flip that switch, just take a second to remember the silent guardians. It's not just the hardware, the relays and the breakers. It's the invisible intelligence and coordination working behind them. This perfectly timed digital dance, happening faster than you can blink, is the only thing standing between our orderly world and total chaos. It really makes you wonder, doesn't it? Our entire world is built on these complex, hidden systems. From the power grid to the internet, air traffic control. What other invisible ballets of engineering are unfolding all around us, every single second, just to maintain the reality that we all take for granted?